So now I'm going to my group going to present about experiment 4, which is vapor compression refrigeration. My group member are Nur Iman Maisarah binti Kamaruzaman, Farishan Nailia Zainal, me Arif Ibrahim Ikhwan Surazi, and Alia Permata Aminuddin.
Hi, Assalamualaikum. My name is Farishan Zainal, and I will start a presentation with the abstract of this experiment. So this experiment is conducted to determine the coefficient of performance, COP, for vapor compression cooling system. In this experiment, the water was set to the condenser and the evaporator at certain flow rates. Then the temperature for T1 and T7 were recorded following the readings of pressure at the condenser and the evaporator. Then from the result, we have obtained the rate of heat transfer occurred at the evaporator and condenser for the 5 tests. We also had discussed the effects of changing the condenser flow rates for T1 to T6 after the graph was plotted.
Assalamualaikum warahmatullahi wabarakatuh. My name is Naima Maisara and I will be explaining the objective and the introduction. So, the objective of this experiment is to determine the coefficient of performance for vapor compression cooling system. Vapor compression refrigeration system are commonly used in industrial facilities to create environments conducive to the preservation and safe storage of products. A device that performs this function may also be called an air conditioner, refrigerator, air source heat pump, geothermal heat pump, or chiller. The compression refrigeration cycle consists of circulating a liquid refrigerant through 4 stages of a closed system, which are compression, condensation, expansion or throttling, and evaporation processes. As the refrigerant circulates through the system, it is alternately compressed and expanded, changing its state from a liquid to a vapor. As the refrigerant changes state, heat is absorbed and expelled by the system, lowering the temperature of the conditioned space.
For the theory, vapor compression refrigeration or cooling system applies a heat engine in which the heat energy is taken from a cold temperature or low temperature into a hot temperature or high temperature. Work is necessary to do on the process or system to have heat transfer. The figure below clearly shows how work applied to the system. As you can see, the red is the hot temperature and for the blue is the cold temperature. So for the calculation or formula, for coefficient of performance refrigerator based on the following equation as we have learned on the thermodynamics, COPR or refrigerator is equal to desired output divided by required input equal to cooling effect divided by work input equal to QL divided by work net in equal to QL divided by QH minus QL. For the methodology, the apparatus is compressor, evaporator, main switch, valve, condenser, temperature selector switch, and there is the temperature indicator. The procedure, step 1, open the valve, and then for step 2, turn on the water pipe, then set the water flow to the evaporator and condenser at the rate of 26 grams per second, and then step 4, switch on the device. Step 5, allow cooling system to be stable approximately 10 minutes. So we have to count it until 10 minutes. And then for step 6, after that, record the readings of temperature T1, T2, T3, and T4 by adjusting the temperature selector switch and take the readings at temperature indicator. Step 7, take the reading of pressure gauge of condenser and pressure gauge of evaporator. As you can see there is the evaporator and there is the condenser. Step 8, after that, record the readings of T5, T6, and T7 manually. Repeat the experiment by changing the flow rate of water condenser between 26 to 4 grams per second. Then, in this experiment, we need 4 sets of experiment. Step 9, when the experiment is done, Make sure the device is closed in accordance with this procedure. Set the flow rate of condenser at evaporator to 0, then switch off the main switch. The step 10, last step. After 1 minute, turn off the water supply pipe, and then after 1 minute, close the valve to shutdown position. So that's all for the methodology.
So now I'm going to talk about the discussion. For the discussion, number 1 is calculate the rate of heat that occurs in the evaporator and the condenser for the 5 tests run and discuss the result. So as you can see, this is our calculation for the rate of heat transfer in evaporator by using table A4 and interpolation of data. We're using the ml is equal to 0.02 kilogram per second. After that, we can get all of our rate of heat transfer. For Q1 is 36.47, Q2 63.35, Q3 63.33, Q4 63.31, and Q5 63.26. Next, we're going to calculate the rate of heat transfer in condenser. For Q1 is negative 62.82, Q2 negative 52.74, Q3 negative 43.06, Q4 negative 33.47, and Q5 is negative 23.89. So for the coefficient of performance of the refrigerator, we calculate it by using QL over QH minus QL. And for experiment 1, we got the coefficient of performance of the refrigerator is 0.5. For experiment 2, we get 0.54. For experiment 3, we got 0.62. Experiment 4, 0.65. And experiment 5, 0.72. So for number 2, we're going to explain the effect of changing the condenser flow rate of T1 to T6 to compressor power. We will draw the graph and discuss the results. As you can see from the graph, this is what we plot by using the result we obtained. From figure 1, we can see that when the condenser flow rate increased, T5 was increased. This is because the heat transfer rate in the condenser is inversely proportional to the water flow rate. The temperature of water passing through the evaporator and condenser is affected by changes in condenser flow rate. We can also see from the graph that the values of T1, T2, T3, T5, and T6 are nearly constant for each reading. T1, T2, T3, T5, and T6 had very slight changes because the refrigerant R141B that enter and leave the evaporator is saturated. Therefore, the temperature T1 and T2 are almost unaffected by changes in condenser flow rate. T3 and T4 values are affected by changes in condenser flow rate because of the transferring processes. Their value decrease as the condenser flow rate rise. So next is compressor versus condenser flow rate. As you can see, this is what we get. So now for the explanation. Based on the figure 2, we can say that compressor power is decreased from 12 grams per second until 22 grams per second. But then it increases from 22 grams per second until 26 grams per second. The rate of heat transfer for the condenser has the negative value because the condenser cooling process. Flow rates in the condenser directly proportional to the rate of the heat transfer in the condenser. Pressure in the compressor was positive value, but in the evaporator was negative value. This is because in the absolute pressure in the compressor, it was absolute pressure in the compressor, but it is gauge pressure in the evaporator. That's all from me.
As a conclusion, the value of COP for vapor compressor cooling system is determined. From the discussion, we can see that the relationship between coefficient of performance, COP, is directly proportional to the rate of heat transfer, QL. The value of COP increases when the QL increases, while the flow rate of the condenser decreases. Other than that, we can conclude that the condenser flow rate is inversely proportional to the temperature, as when temperature increases, the condenser flow rate decreases. The reason behind the small changes in temperature when the flow rate increases might be caused by errors occurred, such as parallax error, where the eyes are not perpendicular to the scale, and methodology error, where the cooling system was not stable during the 10 minutes checking. For the relationship between the rate of heat transfer and the condenser flow rate in the condenser is directly proportional, as the rate of heat transfer decreases when the flow rate decreases. That's all from group 2. Thank you.